So I'm going over the homework for next week, which is to review. And I just did the 4 problems on page 8, which were not recorded, but for now on everything. Okay. All right. Here's some exercises on page 12.
Professor, the recording that we missed, could you please upload that on course material?
Yes, I will. I'll make a PDF copy of the pages and I'll put them on under course materials. Thank you.
Thank you very much. Really appreciate it, Professor.
Sure. Okay. Page 14, no, page 12. All right. So in exercise number 1, we have 3 vectors, 1, 1, 3, 5, and 11, 4. And we want to show that these vectors are linearly dependent. That means I want to compute scalars x1, x2, x3, not all 0, such that x1 v1 plus x2 v2 plus x3 v3 is equal to the 0 vector. So x1 v1 is this, x2 v2 is this, x3 v3, that's this. So this vector is x1, x1. This vector is 3x2, 5x2. This vector is 11x3, 4x3. So when you add these vectors, you get x1 plus 3x2 plus 11x3 and x1 plus 5x2 plus 4x3. And I want to find values of x1 and x2 such that this is the 0 vector. That means I want to solve the equations x1 plus 3x2 plus 11x3 equals 0 and x1 plus 5x2 plus 4x3 equals 0. If I subtract these equations, I get minus 2x2 plus 7x3 equals 0. So 2x2 has to be equal to 7x3. And let's see. I really just need to find some solution which is not all 0. So according to this, x3 has to equal 2/7 x2. So if I plug this into these equations, what does that give me? It gives me x1 plus 3x2 plus 11 times this, which is 22 over 7x2, which is equal to x1 plus, this is 20 plus 43 over 7x2. That has to equal 0. And in the second equation, I get x1 plus 5x2 plus 4 times this plus 8 over 7x2, which is x1 plus 43 over 7x2 equals 0. So I could let x2 equals 7, x1 equals minus 43, x3 equal 2. I'm just solving these 2 equations and 3 unknowns. And I want to find a non-trivial or non-zero solution. So this is a solution. You get minus 43 plus 6 is minus 37. Let me just double check my arithmetic if this doesn't look correct. 1, 3, 11, 1, 5, 4. So x1 plus 3x2 plus 11x3 equals 0. x1 plus 5x2 plus 4x3 equals 0. I just have to find the solution of this somehow. If I subtract, I get minus 2x2 plus 7x3 equals 0, or 2x2 equals 7x3. And if I let x2 equal 7 and x3 equal 2, then 3x2 is 21 plus 11 x3 is 22. 21 plus 22 is 43. So x1 should be minus 43. 5x2 is 35 plus 8 is 43. x1 equals minus 43. Yeah, so this is completely correct. And I solved the problem. I found numbers x1, x2, and x3 that satisfied this equation. Any questions about this? Problem 2 is similar, but in 3 dimensions.
That up real quick.
Yeah.
Sorry. Yeah, I didn't get that last part. Thank you.
Problem 2 is similar, but in 3 dimensions instead of in 2 dimensions. So in problem 2, on page 12, we have 4 vectors in R3, 2, 2, 1, minus 4, minus 3, minus 1, 6, 9, 8, 10, 21, 9. Now we know these are all in R3. So we know R3 is 3-dimensional, so any 4 vectors must be linearly independent. So there have to be scalars, x1 up to x4, such that x1 v1 plus x2 v2 plus x3 v3 plus x4 v4 equals the 0 vector. So what is this? x1 v1, that's 2x1, 2 x1, x1. x2 v2 is minus 4 x2 minus 3x2 minus x2. x3 v3 is 6x3, 9x3, 8x3. x4 v4 is 10x4, 21x4, 9x4. When you add these together, you get a vector whose first coordinate is 2x1 minus 4x2 plus 6x3 plus 10x4. 2x1 minus 3x2 plus 9x3 plus 21x4. x1 minus x2 plus 8x3 plus 9x4. And this has to be equal to 0, the 0 vector. So we have to satisfy 3 linear equations in 4 variables. 2x1 minus 4x2 plus 6x3 plus 10x4 equals 0. 2x1 minus 3x2 plus 9x3 plus 21x4 equals 0. x1 minus x2 plus 8x3 plus 9x4 equals 0. You have to find the solution of these 3 equations and 4 unknowns. So the different ways that you can do it, for example, you can try to eliminate the variable x1. So if you take the first equation and subtract the second equation, you get, well, actually, let me do it the other way because I get positive numbers. I take the second equation minus the first equation. I get x2 plus 3x3 plus 11x4 equals 0. And if I take the second equation and I subtract 2 times the third equation, so I multiply this equation by 2, I get 2x1 minus 2x2 plus 16x3 plus 18x4. It's just multiplying this equation by 2 equals 0. If I take this equation minus the second equation, the x1's cancel. Minus 2 plus 3, I get x2. 16 minus 9 is 7. 18 minus 21 is minus 3. It's 4. So I get now 2 equations in 3 variables. If I take the first equation and subtract it from the second, I get 4x3 minus 14x4 equals 0. So a non-zero solution of this, I could take x3 equal to 14 and x4 equal to 4. And then x2, which is going to equal this equals 0. So x2 is minus 3x3 minus 11x4. This is minus 3 times 14 minus 42 minus 11 times 4 minus 44. That's minus 86. And then x1 from this equation, x1 is equal to, if I bring this to the other side, x2 minus 8x3 minus 9x4. So that's minus 86 minus 8 times 14 minus 9 times 4. What is that? Minus 86 minus 132 minus 36. So this is 86, 168. It might be minus 254. In any case, I have values for x1, x2, x3, and x4, and I solve the problem. Okay, any questions? I mean, the setting up part is the hard part, or that's the part that's new. Solving these equations is just high school algebra and hard work. Okay. Let's see, that was exercise 2. What about exercise 4? Okay, the question is, they're given sets of vectors. Are they linearly dependent or linearly independent? So in part A, we have the vectors 0, 2, and 3, 0. So suppose you can write the 0 vector as some linear combination of these two vectors. That this is 0, 2x plus 3y, 0. So this is the vector 3y, 2x. And the only way this is the 0 vector is when both of these coordinates are 0, so x and y have to be 0. So it's only the trivial linear combination of these two vectors that produces the 0 vector. So 0, 2, and 3, 0 are linearly independent. No linear combination of them is 0. Any questions about that? Part 3, we have the vectors 1, 2, and 2, 1. And we want to know, when does it happen that a linear combination of the vectors 1, 2, and 2, 1 gives 0? See, this is the vector x, 2x. This is the vector 2y, y. So x plus 2y, 2x plus y. When is that equal to 0? So we're solving two equations and two unknowns. X plus 2y equals 0, and 2x plus y equals 0. But this says that x is equal to minus 2y. So 2x plus y is 2 times minus 2y plus y is minus 3y. That's equal to 0 if and only if y equals 0. And if y is 0, x equals 0. So the only linear combination of these two vectors that gives the 0 vector is x and y equal to 0. So these vectors are independent. Part C is very easy. You have the vector 0, 0, and 2, 1. If I multiply this vector by 1 and this vector by 0, I get 0, 0. So this is a linear combination of the two vectors. And the coefficients I'm multiplying by are not both 0. So these vectors are dependent. And for the vectors 1, 2, 2, 3, and 3, 4, again, we know these are dependent because you cannot have 3 linearly independent vectors in a two-dimensional vector space. If you want to do this by solving equations, you would say, well, suppose x times the first vector, y times the second vector, and z times the third vector, which is x plus 2y plus 3z, 2x plus 3y plus 4z. Find a solution, x, y, and z, if this vector is the 0 vector. Which means we're solving two equations and two unknowns. X plus 2y plus 3z equals 0. 2x plus 3y plus 4z equals 0. you multiply the first equation by 2 and subtract it from the second, and subtract the second from it, you would get 2x minus 2x, 4y minus 3y, 6y minus 4z. You get y plus 2z equals 0. So if you let z equal to 1 and y equal to minus 2, and then this is minus 4 plus 3 minus 1. You have x equal to 1. This should be a solution. Of this vector equation. In fact, it's easy to see it is, because if you add 1, 2, and 3, 4, you get 4, 6, which is exactly twice that. So a 1 minus 2 and a 1 will give you the 0 back. So these are computational problems, which requires that you understand the concepts and have the technical skill to solve some linear equations, which is what one does in linear algebra. Question? Okay. Let's see, that's number 4. Let me skip 5 for the moment, because it's just a lot more calculation, and look at 7 and 13. So problem number 7. Suppose you have vectors v1, v2 up to v sub k in Rn, and v sub I equals 0 for some I. Show these vectors are linearly dependent. And the proof is simply the following. Suppose I take 0 times v1, 0 times v2, 0 times v sub I minus 1, 1 times v sub I, 0 times v sub I plus 1, 0 times v sub n. So I take this linear combination of these, so this should be a k. And this linear combination of the k vectors, where every coefficient is 0, except the I where the coefficient is 1. But the vector vi is the 0 vector. So this is all just 0. And this is a non-trivial linear combination, because even though most of the coordinates, most of the coefficients are 0, they're not all 0. I have a 1 here. So that's a proof of linear dependence. Vectors are linearly dependent, linearly independent if the only linear combination of them equal to 0 is the 0 combination. It's not all 0. What about problem 13? Suppose I take W1 to be the subspace generated by the vector E1. So all scalar multiples of the vector E1. E1 is the vector 1, 0. E2 is the vector 0, 1. W2 is all scalar multiples of E2. This is all vectors where the first coordinate is, where the second coordinate is 0. This is all vectors where the first coordinate is 0. And W1 intersect W2, it has to be a vector where the first and the second coordinates are 0. It's just a 0 vector. So W1 intersect W2 is just a 0 vector. But W1 union W2 is not a subspace, because the vector E1 is 1, 0. It's in W1. The vector E2, so it's contained in W1 union W2. The vector E2 is 0, 1. That's in W2. So that's contained in the union of these two subspaces. But what is E1 plus E2? That's 1, 0 plus 0, 1. That's the vector 1, 1. And this is not in W1 union W2. Because the union of those two subspaces is vectors that have at least one coordinate equal to 0. And this vector has no coordinate equal to 0. So W1 union W2 is not closed under vector addition. So not a subspace. That's the proof. Any questions about these? All right, so the next set of problems is on page 19. And we have to do exercises 1 to 6. So number 1, we want to describe subspaces generated by the following sets and compute their dimensions. So S1 consists of the two vectors 1, 0 and 0, 2. And the subspace generated by S1 is the set of all linear combinations of these two vectors, x times 1, 0 plus y times 0, 2. So any vector of this form, which is x0 plus 0, 2, 1, which is x, 2, 1. But this is all two-dimensional vectors. Right? So, for example, if you wanted to write 7, 9, this is 7, 2 times 19 halves. This would be 7 times the vector 1, 0, plus 19 halves times the vector 0, 2. Okay, 9. So the subspace generated by S1, I'll write it like this, is all of R2, and the dimension is equal to 2, because R2 is 2-dimensional. Any questions about that? So this is part A. What about part B? So S2 is the set that consists of the vectors 1, 1, and 1 minus 1. So the subspace generated by S2 is all vectors of the form x times 1, 1 plus y times 1 minus 1, which is the vector x plus y, x minus y, for all real numbers, x and 1. So the question is, given a vector t1, t2 in R2, can you write this in the form x plus y, x minus y? And you choose x and y to solve this vector equation, which is the same as the linear equations, x plus y equal t1, x minus y equal t2. And you can solve these equations. If you add them, you get 2x is t1 plus t2, where x is t1 plus t2 over 2. If you subtract them, you get 2y is t1 minus t2, or y is t1 minus t2 over 2. So for any vector t1, t2 in R2, if I take t1 plus t2 over 2, that's scalar times the vector 1, 1, plus the scalar t1 minus t2 over 2 times the vector 1 minus 1. Right? That's a valid equation. That works. So the subspace generated by these two vectors is all of R2 and therefore 2-dimensional. Part A and part B. What about part C? In part C, S3 consists of two vectors, the 0 vector and the vector 1 minus 1. If you take a linear combination of these, any number times the 0 vector is 0. So this is just the vector y minus 1. So the subspace generated by these set of vectors S3 is just all scalar multiples of 1 minus 1, vector y minus 1. And this is 1-dimensional. The basis is 1 minus 1. And finally, in part D, S4 consists of the following three vectors: 1, 1, 1 minus 1, minus 1, 1, which is contained in R2. So the subspace it generates is contained in R2. But we already saw that just the first two vectors gives you all of R2. So the subspace that these generate is R2, and we can take the first two vectors as a basis because we made it good. Any questions about that? Then we jump to number 3. So in R3, we can take the basis of 3 vectors, v1, v2, and v3, where v1 is the vector 1, 1, 0, v2 is the vector 1, 0, 1, and v3 is the vector 0, 1, 1. And if I take the vector 3, 4, 5, I can write this as some linear combination of these 3 vectors. We just write it as x times 1, 1, 0 plus y times 1, 0, 1 plus z times 0, 1, 1. And what is called the coordinate vector of this vector v with respect to the basis b is this vector x, y, z. X times the first, y times the second, and z times the third basis vector. So we have to calculate what x, y, and z are. X times this first vector is x, x, 0. This is the vector y, 0, y. And this is the vector 0, z, z. So I get x plus y, x plus z, y plus z. And that's supposed to equal 3, 4, 5. So I have to solve the equations. X plus y equals 3. X plus z equals 4. Y plus z equals 5. So, for example, I can eliminate the x by subtracting the second equation from the first. I get y minus z is minus 1. This equation with y plus z equals 5. If I add, I get 2y equals 4. So y equals 2. If y equals 2, z equals 3. And if y equals 2, x equals 1. So the coordinate vector for v with respect to the spaces b, x, y, z is the vector 1, 2, 3. Any questions about that? And the second part of this problem is done similarly, and for some reason I actually put the answer in. so you can check your work. This is problem 3. What about problem 4? So we have W1 and W2 subspaces of Rn with W1 contained in W2. We want to show that these subspaces are equal if and only if they have the same dimension. Well, of course, in one direction, it's very simple. If W1 equals W2, then of course they have the same dimension. Only one space have the same dimension. But suppose we know that the dimension of W1 equals the dimension of W2. So suppose you let B1 be the basis for W1. But here's sort of a picture. Here's W1 contained in W2, all sitting in Rn. W2 is not equal to W1, then there exists a vector W sub 2, which is in this bigger subspace W2, and not in W1. I claim that if I take B, the basis for W1, union the vector W2, I claim this set is linearly independent. Let's just suppose that this basis B for W1 consists of vectors B1, B2, up to B sub K. So the dimension of W1 is K. If W2 is not in W1, suppose we have some linear combination, x1 v1 plus x2 v2 plus x sub k v sub k plus y times this vector W2 equal to the 0 vector. If y is not 0, then you can solve this equation for W2. You get y W2 is minus x1 v1 minus xk vk. But this is a vector in W1, which is impossible because W2 is not in W1. So y has to be 0, but then all the other x's are 0, because these are this is a basis. These vectors are linearly independent. And in that case, the dimension of W2 is at least k plus 1. So I have k plus 1 linearly independent vectors, and that contradicts the fact that the dimension of W1 equals the dimension of W2. So this is a proof. Right, a nice proof of that. Any questions about this? Let's do one more problem, then we'll be done for today. This is number 5. So I'm working in R3, and W1 is the subspace generated by the vectors 1, 0, 0, and 0, 0, 1. So this is the set of all vectors that you can write as a linear combination of these two vectors, which is x, 0, z. It's all vectors where the second coordinate is 0. And W2 is the subspace generated by the vectors 1, 0, 0, and 1, 1, 0. And the linear combination of these vectors is something that looks like x plus y, y, 0. So you can choose x and y arbitrarily. So this is all vectors where the third coordinate is 0. So what is W1 intersect W2? It's all vectors for both the second and the third coordinates are 0. So it can only be vectors in the form x times 1, 0, 0. Here's a typo there. So, yeah, so this is part A, this is part B, this is part C, and parts D and E, where it says W1 union W2, it should be W1 plus W2. The union of two subspaces is not a subspace. Subspace, and this is equal to R2. Because W1, you can get all vectors where the second coordinate is 0. In W2, you can get all vectors where the first and the third coordinates are 0. You choose X and Y correctly. I think together you can get all that. So, and in fact, the dimension of W1 plus W2 is equal to 3. The dimension of W1 intersect W2 is equal to 1. The dimension of W1 is 2. The dimension of W2 is 2. And the relation that is written down to prove is simply saying that 3 plus 1 equals 2 plus 2. So all this exercise I was asking you to just double check that 2 + 2 is 4. Any questions about these? All right, so there still are some problems on page 45 and 53 of the notes. I'll go over them on Monday. Again, I remind you, I have office hours basically every day, so you're welcome to log in anytime and ask a question. Anything else before we go? Okay. It's supposed to be a nice day outside.
Professor,
Yes.
how many questions are going to be on the test?
I don't know, 6 or 7 probably.
Okay,
There's always some extra credit also, so you can leave out a problem or 2 and still do very well.
thank you.
Okay.
Professor,
Yes.
yeah, the exam time is during class time, right?
Yes.
Okay. So time is up when class is over.
11 to 1 is the exam.
Okay, thank you.
I mean,
Professor.
officially, it's 11 to 12:40, but it takes a while to convert your handwritten pages to a PDF file and upload it to Blackboard.
Professor, will you give partial credit like with the problems, or is it just like if you get it right, you get it right, or if you get it
No,
wrong, you
no,
get it
there's
wrong?
partial credit.
Okay, thank you.
Anything else? Okay, we're done for the morning. Stay well, everyone. Next class is Monday. Bye.